in today's tutorial we'll take on some problems on basics of AC circuit, right? So the first question is like this: express the sinusoidal time function by Phasor representation. Okay, and then also we need to label resistors, inductors and capacitors by their impedances or admittances and find V0. V0 is the voltage across the capacitance. Now the voltage is given in the time domain as Vs is equal to 6 sin 2t V. So we just have to remember this whenever a time domain signal is given like this. 6 is the max voltage. Okay, so it's not the R.M.S voltage. Okay, whenever in time domain we specify a sinusoidal like this, it is Vm sin omega t, right? So 6 is Vm. Okay, it's not the R.M.S voltage. So you got to be careful with this Vm and VRMS in your exam. Okay, so always when in the time domain, remember it is Vm. That means it's 6 is the max value of the voltage. Okay. So in the phasor diagram, okay, we just write it 6. Okay, and since it is an phasor, we know how to represent a phasor. It is just magnitude and the angle, and the angle is always cos with respect to the cos. Okay, so it is sin 2t. So that we read discussed in the class. Sin 2t can be written as cos 2t minus 90, so that's why this it does come as minus 90. Had it been 6 cos 2t, this would have been straight away 6 and then no angle or 0, right? Since it is sine, then that is the reason we have minus 90 out here. Okay, and also this is the frequency. Here it's written separately, but this you need not write the frequency, because when we when we solve the problems in phasors, it is frequency is not taken into consideration, assuming that the frequency remains constant. Okay, there is only a single source which is generating a single frequency, so we assume that the frequency is not going to change in this circuit. So that is the reason it is written separately out here, because it is 2t. Okay, now this 2 is 2 pi f. Remember that this is omega, radians per second. Okay, it is not 2 hertz. It is 2 radians per second. If you have to convert it into frequency, you will have to equate this 2 into 2 is equal to 2 pi f. So f would come to the value of f will be 2 divided by 2 pi. Okay, so 1 by pi, that will be the frequency. Omega is 2 radians per second out here, and 1 is going to be represented as 1, and the capacitor of half farad is going to be represented as 1 by j omega c, right? And omega is given as an 2, so that 2 along with it's given as 2 out here, so that 2 and this half gets cancelled, so I have 1 by j, or I can multiply it by j in the numerator and denominator, so minus j square becomes minus 1, and you get a final answer of minus j omega. So this is the phasor representation of this same circuit, which is shown on the right hand side is the phasor, and this is the sinusoidal representation, time based representation, right? And now to find the value of voltage across this capacitance. Okay, so first we can find out the current also. So the net impedance, the total impedance offered by this circuit will be 1 ohm minus j ohm. So 1 minus j into I. Okay, so that is the net impedance into I. Okay, is 6 into this is the voltage. V is equal to, this is Ohm's law, just Ohm's law. So this is the voltage, and this is an 1 minus j, which is the total impedance, that is 1 and minus j into I. Okay, so from here we just take I is equal to 6 minus with angle is minus 90, and 1 minus j can be again represented as root 2 into minus 45. So where did we get this root 2? It is an a square, root of a square plus b square, right? So this we learnt how to convert the polar into polar form into rectangular form, right? So this is a square plus b square, that is an the real part is 1 and imaginary part is 1. So a square plus b square, 1 square plus 1 square root, that is an root 2. and the angle is given by an tan inverse of minus y by x. Okay, so y is -1, so tan inverse -1, which is -45. So we have done this here, right? So now you divide these two. So again we have done this in the class, how to in the how to divide these kind of functions. So this is this gets subtracted and this gets divided. So 3 root 2 and -45, right? So this is the current. Okay, now 3 root 2, is it the RMS value or the max value? Anybody? Shashank? Dheeraj? Anybody? This is the max value of the current. It's not the RMS, because voltage is also we have taken as the max, right? 6 is the max value. So 3 root 3 is the max current value. Okay, so that need to be remembered. So now finding out what is the voltage across the capacitor. So you just have to multiply the impedance into the current here. So impedance is minus j here. So minus j into current. So minus j can be represented as 1 and minus 90. So you multiply these two things. So you get so when you multiply, we know these two gets added up. So this is the voltage across the capacitor. So is it clear to all of you how to solve these kind of problems?
Yes, sir.
Yeah. Okay. So let's take one more example. A sinusoidal alternating current of 6 amperes is flowing through a resistance of 40 ohms. Calculate the average voltage and peak voltage. Now when we say when we specify this, a sinusoidal current of 6 amperes is flowing, or we say the a voltage of 6 volts is applied across a resistor, AC voltage. So when we say like that, remember it is always RMS and not the peak value. Is it clear? So if I go to the previous problem, it says it's defined in an the sinusoidal signal is defined in the time domain, where this 6 is the peak value, right? Okay, because if you see the form, it is Vm sin omega t. So this becomes the peak value. So this is where most of you go wrong in your exams. So remember that this is not the peak value. Okay, whenever we write when the problem is given in like this, okay, when it says a sinusoidal current of 6 amperes or a voltage of 230, what we have in our home, 230 volt is the voltage, AC voltage we get in our home, right? So they are all, when we just say like that, okay, this is the voltage, it means RMS voltage. Okay, so here also 6 amperes means an RMS voltage. So RMS in this case 6 amperes is the RMS current. Okay, so what is the voltage? RMS voltage will be simply a product of these two, right? So I into R on 14. And what is the average value and the peak value? So peak value is peak value will be this into root 2, because RMS value we know that it is 240. RMS value is V peak divided by root 2. So peak value will be other way around, 240 into root 2. Similarly, average value of a sinusoidal. Like I said, if you take an average of a sinusoidal across around for 2 pi duration, it will be 0. But we said in conventionally, when we called an average of a sine value, we take only the average of the positive cycle. From 0 to pi we integrate it. So that we know it is like RMS value divided by 1.11. Okay, this we did in the theory class. Okay, so the RMS value divided by 1.11 will give the V average. Okay, so that comes out to be 216 volts, and the peak value will be RMS into root 2, that is 1.414. So 339.4 volts. Okay, is this okay? Yeah. If you could respond, it would be better. I will know I am still online. Okay. Now this is again the next problem, in which we say convert polar form into rectangular form. So 6 into 30 x plus jy. Okay, so we need to find the value of x and y. Can anybody prompt what could be the answer? X will be, yeah, it will be 6 cos 30.
Cos 30.
Yeah, yeah. and y will be 6 sine 30. Okay, so
6 times.
these are simple, right? X is equal to a cos theta and y is equal to a sine theta. So it will be 6 cos 30 plus j into 6 sine 30. So you get an 5.2j and 3j. So accordingly, so these are pretty simple, straightforward problems. And similarly, from the rectangular, if you want to make it to polar, in that case also, so it will write in a 5.2 plus 3j. So a is the magnitude, so which you get root of x square plus y square. So 5.2 square plus 3 square, which again you get back 6, and theta will be tan inverse y by x. Okay, so y in this case is 3, x plus yj, right? And x is 5.2, so you get an tan 30. So we represent this as an in the vector form 6, and angle is given as 30. So this is how we convert from polar to rectangular. Okay. So now this is again some algebraic manipulations of phasors. Now we have to multiply these two things. Okay, so how is multiplication done? Multiplication of two phasors is done by multiplying the magnitudes and then adding the angles. Okay, so that is how. So z1 into z2 is where z is equal to a and theta. So a1 into a2, and angle will be the sum of the angles. Okay. So here in this case it is 6 into 8, so that is 48, and then this is 30 and minus 45. So 30 and minus 45, we add it, we don't multiply that, we add that, so you get a minus 15. Similarly, division. In the division case, we divide the magnitudes and then we subtract the angles. Okay, so in this case you have 6 and 8. So 6 divided by 8 is 0.75, and you have 30, and this is minus 45. So 30 minus of minus 45, so that gives us 75. So this is how from polar, this is polar division in fact. Okay. Okay, so let's take one more example out here. An electric heating element which has an AC resistance of 60 ohms is connected across an 240 volt AC single phase. Again, you got to remember, in this case 240 is the R.M.S value. Okay. Now the question goes like this: calculate the current drawn from the supply and the power consumed by the heating element. Also draw the corresponding phasor diagram showing the phase relationship between the current and the voltage. Okay, so first of all, this is R.M.S voltage and this is the resistance. So this problem is pretty simple. This supply current would be merely just voltage divided by resistance. You get 4. So now this I is also an R.M.S value. Okay, and then the active power is, because here it says this is the total AC resistance. So the active power will be I square R or V into I or V square by R. You can use any of the formulas. You get 960 watts. Okay. Again, because this is R.M.S value, so you can straight away use this formulas out here. Okay, and since it's an resistive element, the current and the voltage going through the resistance will be in phase. Okay, so you can make the phasor diagram. Okay, both showing it that both are having the same phase. So I is equal to 4 ampere, V is equal to 240 ampere. So they both are in the same direction. That means there is no phase difference between these two signals. So that is true for an resistance, right? In resistance we learned that there will be no phase difference between the voltage and current. Okay. So we'll take on one more problem. Here it says a sinusoidal voltage is defined as Vt is equal to 100 cos omega t plus 30 is connected to a pure resistance of 50 ohms. Determine its impedance and peak value of the current flowing through the circuit and draw the corresponding phase diagram. Okay, now in this case 100 is the peak voltage which is going to be applied across the resistance out here. Okay. The sinusoidal voltage will be same for the supply in the pure resistive circuit, it says. Okay, because there is no phase difference here because it's a pure resistive circuit. Converting this into phasor representation is, we can represent this as phasor 100 and an angle 30. This is the phasor representation. Okay, VR here doesn't indicate R.M.S. Okay, here in this case. Okay, VR means voltage across the resistance, and here this is not an R.M.S. value, this is the peak value which we are speaking here. Okay, so we need to be careful with these notations. So applying Ohm's law, we get IR is equal to V divided by R, or 2 R is given as 50, so 2 and 30. Again here 2 is the peak value, okay, of the current. Okay, so the corresponding this is the peak value of the current. Okay, it says determine the peak value of the current. Peak value will be 2 out here. Okay, magnitude would be 2 out here. So now if you see the phasor diagram, it is similar to that of the previous problem. Only thing is this signal with respect to time. So we have assumed, okay, some 0 time somewhere we have fixed, and we are assuming that this signal is lagging by 30 degree. So leading by 30 degree. So that is why this voltage is shown leading by 30 degree. However, since it's an pure resistive circuit, the current also will follow the voltage. So hence that is also leading by 30 degree. So this is how we draw the phasor diagram. Is it clear to all of you? Okay. Okay. Now let's yeah. Okay. Let's take an inductive circuit and do the analysis. Here in the following circuit, the supply again the supply voltage is defined as Vt is equal to 325 sine. Okay, this is the omega t and minus 30. That means the voltage is lagging by 30 degrees, lagging with respect to some reference. Okay, at t is equal to 0, it is lagging by 30, and the value of L is also given. Now determine the value of the R.M.S. current. Okay, the question says, and it's not asking for the peak current, it's asking for to determine the value of the R.M.S. current flowing through the coil and draw the resulting phasor. Okay, so this is the voltage which is given here, right? I am at the cost of repetition, I am telling you this. When you are attempting your exam questions, be careful with what is being asked, whether it is the peak value is being asked or it's the R.M.S. value which is being asked. Okay. So whenever this voltage is defined in the form of a sinusoidal signal like this, time domain sinusoidal signal, this is the max value and not the R.M.S. value. Okay, so we got to remember these small things. Okay, so Vt is equal to this is the circuit diagram which is given here. Now since we are interested in R.M.S. value, so we convert this 325 into R.M.S. value in the phasor. So it is 325 divided by root 2, you get 230. Okay, this is what commercially we get in our home also. We keep telling 230 volts AC, 238 volts AC, but the peak value will be 325. Okay, this is what we have in our homes, the 50 hertz 230 volts supply. Okay, so 230 and minus 30 is shown here. Okay, that minus 30 comes because it's defined here as an phase lag of 30, so that minus 30. So the inductive reactance can be calculated by L omega. Unlike a resistance, for an inductance it is an frequency dependent. The reactance offered by an inductance is frequency dependent, given by omega L. So omega is 314. Okay, now if you see this equation, this is omega t. Okay, this is not f, this is omega t. Okay, or 2 pi ft. So this omega, the 314 is omega. So I write an 300 omega into L, which is given as 2.2 Henry. So you get 690 ohms. So the R.M.S. current will be VL divided by JXL. So this is 690. Since it's an inductor, okay, we write. And if you see the current, it's 90 out here, right? Because it's an inductor JXL, right? So that is the reason you have this J is being represented in the phasor as 90. So this is so you divide these two, so you get this answer. Okay. When we do it in the phasor representation, so this is a zero reference. We know the voltage is it is given as it is going to lag by 30. So we draw a phasor which is lagging by 30, and we know the current will be lagging the voltage by another 90 degree. So from here another 90, so that is that we get it as minus 120. So this is the current, okay, and this is, so you need to be clear how to draw this phasor diagrams also. Okay, this is also an important thing. So which is how to draw the current phasor diagrams. Okay, is this clear to all of you? Okay.
Yes, sir.
Okay, then we move forward. Now a coil has a resistance. Here you have a series R and L. So you have a 30 ohms inductance and 0.5 Henry. If the current is flowing through the coil is 4 amperes, it's given. What will be the R.M.S value of the supply voltage? Frequency is given as 50 hertz. Now here again, since it's given current is 4 amperes, and it means it is 4 is the R.M.S value here. Okay, it's not the peak value. Okay, so it is 4 amperes current. So we need to find out what is the R.M.S supply voltage. So this is also some, you just have to find out the impedance and multiply it with the current. Okay, so to find the impedance, it is L. We need to know the frequency. So 2 pi f. Okay, now this is not omega, it is the frequency. 50 hertz is the frequency, not omega. So we need to use this formula 2 pi f. So 2 pi into 50, and L is given as 0.5. So you get 157 ohm, and this is known, this is given as 30. So so the total impedance Z will be 30 square plus 150 square. 157 we got the value of XL. So you get 159.8. And the angle will be the phase tan inverse phi is equal to XL divided by RL. This is again we learnt in the theory, XL divided by R. So 157 divided by 30, you get this angle, right? So once we know the value of Z and the angle, we can compute the current easily. The total voltage across each of them, it is shown here. I into the total impedance will give the total voltage, and I into R will give the voltage across the resistance, and I into L, XL will give the voltage across the inductor. Okay, so you have an I, V and L, and the sum of these two voltages will be the V source, like the sum of the voltage, the if you do this vector addition of the voltage across the resistance and voltage across the inductor, so we are going to get the total voltage which is available from the source. Okay, is it okay? Abhinav, can you just mute your mic? It's picking up some noise. Yeah.
Sorry, sir.
Yeah. Okay. So this is the last example which we are going to take, and this is single AC supplies voltage defined as, again that it's defined in the time domain, is connected to a pure capacitor. Okay, 200 microfarad. Determine the value of the current flowing into the capacitor and the resulting phasor diagram. Okay, so this is the voltage which is given here. Now in all these problems we need to just find out the impedance. Again, like an inductor, in a capacitor the impedance is an frequency dependent component. So you have j omega into C. This is the formula for the impedance of the capacitor. So omega is given here as 314 out here. So 314 into 200 microfarad. So since there is a j in the denominator, you have a phase of minus 90 out here, right? So the current in the capacitor will be the applied voltage divided by, so applied voltage is 240 here, so 240, so 15, so you and this is 16, so this 16, so they get divided, and you have 50, and these gets added up. So this minus 90 goes to the numerator as plus 90, and minus 20 you already have there, so it becomes 70. Okay, now here again remember, since we have taken it as 240 out here, so this means this is the peak value of the current. Okay, so we need to be careful depending on what question is being asked. So here in this particular thing, this is the peak value. If I have to find out the RMS value for any reason, I can divide it by root 2. Okay. So this is how the phasor representation. So we know this is the voltage is lagging by 20. So we put this is the 0 reference. So the applied voltage we are showing it lagging by 20. And now in the current in a capacitor always leads the voltage by 90. So if you see when we did the inductor, we drew the load current lagging the voltage by 90 degree, whereas in the capacitor we know it is going to lead by 90 degrees. So from here it's going to lead. So this minus 20 and 70, 90. Okay, so this is going to lead. So this is how the in the phasor representation of the current and voltage. Okay, so that's all for today. If you have any doubts, you can ask me now. Okay, thanks a lot.